Hello, everyone. This is the lecture for section 2.5, Physical Applications. So in this section, we're going to handle a couple of things that is going to require some knowledge from outside of this course. We're going to need a fair amount of stuff from our first semester of calculus, or sorry, first semester of physics. Okay. I'll try to cover the best I can some of these physical definitions while we're moving along, right? Um, Hopefully, since you guys are all in Calc 2, you might be taking either concurrently or you've probably taken first semester physics before. Okay. Um, Hopefully these sort of resonate with people. Maybe people can remember them. If not, at least you have my explanations to sort of get you going here. Okay. The three topics that we're going to need are these three right here. The mass density, so mass and density. The second one's going to be force, and the last one's going to be work. Okay, so like I said, these are three topics that you would usually cover in a first semester physics class. Okay, so now let's go ahead and get started with mass density first. Okay, like I said, I'll provide a definition at least for what we need so we can run through the calculus with it. Okay, so the definition that I'm going to do right now is just of mass and of density. The mass of an object is sort of like a dimensionless quantity that represents the matter of an object, how much stuff is in an object. Okay, don't get it confused with weight. Weight requires you to have some sort of gravity applied to it, right? So this is just how much stuff is there. Okay. Um, the definition for density, okay, and what I'm going to be using on a sort of semi regular basis here is this Greek letter rho for the density, right? Is the substance mass per unit volume. So if we choose out a particular amount of volume, an amount of space, right? How much stuff for this object is in that amount of space, okay? That's what we call density, okay? So the equation for density, right, is this right here. Rho is some mass divided by the volume, okay? Okay, so the way that we visualize sort of what density is, right, is technically sort of like it says in the definition, right? How much stuff is there in a specific amount of a volume? Okay, so picture two identical cubes, right? One made out of metal and the other made out of styrofoam, right? Um, Obviously the metal one is probably going to weigh a whole lot more, right, than the styrofoam, right? Since the metal is denser than the styrofoam, the metal will feel heavier, right, even though both of them have the same shape. Okay. Now, um, unfortunately, within the same material, so we can have certain materials that we can have the same exact shape for, right, but their weights might be different. Okay, aka their densities might be a little different. Okay, so take, for example, the example that I give here is Swiss cheese, right? You can have a piece of Swiss cheese that has more holes than the other one, right? So, and the Swiss cheese will be denser than, right? If you have two similar sized sort of squares of Swiss cheese, one of the squares of Swiss cheese might be denser than the other one. It might have more holes in it. Okay, cool. We're going to use a variation of our density equation. Okay, and it's going to be this one right here. Okay, so now let's get into the calculus portions of it. So let's simplify our theory for a little bit. Let's move it down just to one dimension. Okay, suppose that rho of x, right, is the density of a one-dimensional shape, like a rod of some sort, right? A piece of metal or rebar, right? Over some interval AB. Okay. We can define our regular partition over this rod, and we can get some subintervals, right? So this is our A, right? And this is our B. That's how far out it goes, right? So A to B. Okay, and this is my x of 0, and this is my x of n, right? And we can go ahead, here's our strip, right? We can go ahead and divide this up into a regular partition, smaller little itty bitty pieces, right? And in particular, we can get, I'm going to concentrate a little bit on this, x of I minus 1, x of I. I'm going to concentrate on a specific little piece, okay? Since this is a regular partition, excuse me, this is still delta x, which is my b minus a divided by n, okay? So let's say we want to find the mass of our rod. Let's say we want to find the mass of this entire rod that's up here, right? So the idea is that because the density changes over the rod, right? Each little piece, right, will have a different mass. Okay, since our density changes across the rod, okay, the mass will be different, right, for each little chunk. Okay, but that sort of gets solved when we sort of divvy it up here, right? Let me actually undo that. So let's take this piece right here, right? So we're talking about this piece right here, okay? The mass for this little piece mi, right, is going to be equal to the rho of xi star times my delta x. So the mass of this little piece right here, just this little piece right here, right, should be, if I divvy this up, right, there's got to be an xi in here, right? I can plug that xi into my rho function, right, for the density at that particular point, and then multiply it by however long, right? So the mass of this little piece right here is supposed to be just this right here, right? So it stands to reason, right, as we've been doing before, that if this is the mass for one little piece, right, we can do the exact same sort of calculation over all of the pieces for our rod, right, and then add them up, and we get the mass of the entire rod, right? This is how we get the mass of something, right, where the density is not equal throughout the whole thing, right, where the density is changing depending on where we are at on our rod, right? So that's where we get this right here. So the mass of an object is the sum of all those little mi's, all of those little smaller masses. And all of those little smaller masses are given by that expression right there, rho of some xi times delta x. Okay, and as what's been happening before, the second we start divvying up our partitions into something much, much smaller, we end up taking an integral. And that is exactly what happens down here. So notice, right, here is the summation, right? And that is what turns into an integral right there. Cool? Okay. A similar argument here, right, is let's say you had a let's say you had a disk, okay, and it had a specific radial density. So depending on how far out from the middle you went, right, depending on how far out from the middle you went, the density is something different every time, okay? So what do I need? Let me slap down an x and a y, okay? And let's say we wanted to go from here, from 0, right, to some value r, right? Depending on how far out you went, right? Let me go ahead and draw some dotted lines here for, right? So this is defined, right, by rho of X. The density of that little ring, right, is defined by some rho of X, right? And if you take a look, right, you have to go out an X amount. Okay, so to find the mass of to find the mass of a disk, right, that has a radial density, right, then we use the exact same uh, equation. It's sort of derived the same way. Okay, so let's say we have a disk that has a radius of 4 centimeters and a radial density given by this equation right here, right? And we want to find this disk. Okay, so first of all, what I'm going to do is I'm going to go ahead and graph that thing that's right there. X squared plus 1 divided by 2. Okay, so let me go ahead and bring this down a little bit. Let's do a split screen. So the idea here is this, that if you notice, so what we have on the right-hand side is the graph of rho of X, right? So if you take a look, it goes from 0 to 4. So it only goes up to 4, up to this point right here, right? If you notice, the lightest portion of our disk, right, is close to the center, and it gets heavier on the way out. Okay, since the density is climbing as we go outward on our disk, right, it's going to be heavier on the outsides. Okay, so in order to find my the mass of my disk here, right, I get to go ahead and plug it into that equation that's right above it, right? And we know that this disk is crude drawing here, but we know that it's going out to 4, right? And this radius right here, this radial density, is being defined by my rho X. Okay, so we know that we need to go from 0 to 4, so let's go ahead and start plugging stuff in. Of 2 pi x times my rho of X, which is this thing right here. Square root x squared plus 1 over 2 dx. And that is equal to pi times 0 to 4 x squared plus 1. Okay, and in order to compute this one out, we can do this using u substitution. So if we do u is equal to x squared plus 1, right? Du is going to be 2x dx. So then therefore, du over 2 is going to be my x dx. So if you integrate this all out, let me do at least a substitution here. It's going to be pi integral of the square root of u du over 2, right? And if you go ahead and do the calculus out for this one, you should get pi over 2 times x squared plus 1 to the 3 halves over 3 halves. And we need to evaluate this from 0 to 4. And if you do this outright, 72.35380. Okay. And let me put some dot, dot, dot. So the decimal keeps going. Okay. If you do this using our definite integral calculator, this is the number that you should get. Okay. Double check to make sure that your work is there when you do these. Okay. Next thing that comes up is your quick checks. So go ahead and do the one that's assigned for you. Okay. Moving on, the next section that I want to do is this section on work and force. So the big thing that we're trying to do here is really work. Okay. And before we end up doing anything for work, we need to define force. Okay. Again, these are topics that should show up in your first semester physics courses. If not, if you haven't taken those yet, I'm gonna cover a little bit here. Okay. So the first thing that I want to define is this topic of force. Okay. The force is defined as any kind of push or pull that's exerted on an object. Okay. The equation for it is this right here, at least the most basic version, right? The force applied on an object is equal to the mass of the object times the acceleration that that object sort of feels. Okay. The force is measured in newtons, which is that type of units right there, kilogram meters per second squared, right? The m is the mass of the object, right? And that's measured in kilograms. And the a is the acceleration measured in meters per second squared. Okay. So that is sort of, at least for now, for what we need to do, that is the mathematical explanation for force. Okay. Now, let's get into work. Work is defined as the amount of energy required to move an object when a force is applied to it. Okay. The most basic version of the work equation is this right here. Okay. Work is equal to some force times some distance. Okay. So work is measured in joules. Force we know is measured in newtons, right? And X, that very last X in the equation for work, is measured in meters. Okay, so the idea here is this, that um, sort of a force, right, is an amount of push or pull, right? And the work is the amount of work, work is the amount of push or pull that one exerts over a distance. Okay, that's sort of like the difference here. Okay. Hopefully that makes sense, at least for what we need to do. Now, let's go ahead and get into the calculus of it. Okay. So the problem with force is that just like density, right? Uh, we don't have an even spread of material. Like in density, we don't have an even spread of material sometimes. So certain things might be denser in certain parts, right, than others. Okay. Think back to Swiss cheese. If I go ahead and cut up my Swiss cheese, I might hit a hole, I might not, right? And depending on if I hit a hole or not, right, my density sort of changes, even though I'm taking little pieces out of Swiss cheese, right? Okay, same thing with the force. A force, right, that is applied to an object isn't always constant. Okay, I can't apply, 50 newtons at a constant amount. Okay, usually that force sort of changes. Okay, so that's what we're going to be studying here. So let's say f of x is that force that's applied on an object where x is the position. Okay, and I'm talking about f of x as a function. So depending on a distance x, right, there's a specific force f of x applied to it. Okay, now let's go ahead and take an object and let's apply a force to it. Okay, so let me go to shapes. I'm going to slap down an x-axis right here, and not that color. Hopefully I can change it to, nope, it won't let me. Okay, let me try that again. So let's go from A to B, right? And let's take an object. So here's my box. Let's go ahead and take this box as an object, right? Okay. I'm still gonna do the same thing that I've been doing from before. I'm gonna grab my A to B and divvy up my A to B into regular subpartitions, right? Okay. And I'm gonna particularly look at this spot right here, xi minus 1, xi. This is the xith distance that I'm going to be moving my box, right? And let's suppose that I had my box like right above here, okay? So one last thing that we have to take a note of, right? Since this is a regular partition, my delta x is still my b minus a over n. This is still a fixed width, okay? This is still a fixed amount of distance, right? Okay. So now, let's say, let's say that I want to move this side of my box over here. Okay. That is, I want to be able to move my box across this little piece right here. Okay. And I want to find out how much work it'll take to do that. I want to find out how much work it'll take for me to move my box over that little strip in pink. Okay, that's what we're trying to find. And if we take a look at that, right, that's going to be the ith amount of work, right? It's going to be equal to the force at some xi star that sort of has to belong in here, right? You guys remember that xi star, right? And it needs to travel delta x far. So I need to make my box travel this distance right here, which is delta x. So the work that it's going to take me to move my box over that one little strip from x of I minus 1 to x of I is given by this expression right here. Okay, so it stands to reason now, right, that if I wanted to move my box all the way from A to B, then I can grab all of my works for each little subinterval, right, add them all together, and I get my entire amount of work for moving my box from A to B, right? And that is exactly the argument here. So the work is approximated as the sum of all the little works, the W sub i's, right? And each one of those W sub i's is given by the F of xi star times the x delta x, right? And we just add them all up together, right? And just as before, what we want to do is we want to grab that little partition, those little subintervals, right? And we want to divide them up into smaller and smaller and smaller and smaller little things, right? And the second that we do that, we do an integral, right? So that is my definition for finding the force, or sorry, finding the work, right, of moving something along a segment AB. So it is the limit of the sum of the WI's, which is the limit of the F of XI's times delta X's, and that's what turns into that. Okay. Okay. One of the applications that we're gonna be able to see, at least for now, at least in Calc 2, and once you guys get into Physics 1, if you haven't taken that before, right, is Hooke's Law. Hooke's Law deals with stretching and compressing a spring. And the way that we find out the force that's required to compress or stretch a spring, right, is by this equation right here. Okay. K usually is the characteristic value for a spring. That's usually found by testing. Okay. And at least in this class, I'm going to give you the K, or I'm going to give you enough information to find it. Okay. So the idea here is this. Here's sort of like an anchor. Picture this being a wall, right? And then here's your spring, right? And here's your object, right? So you can do two things here. Um, First of all, let me define this. There's going to be sort of like a line that if you just leave the spring alone, right? That is what's going to be called the equilibrium point, right? Or the point of equilibrium, okay? That if you just leave the spring alone, it's just going to sit there. And wherever it sits, right, that position is called the equilibrium position, okay? Now, um, for the most part, right, if you move this way, we consider this the positive direction. And if you move the other way, we consider this the negative direction. And this is regardless of where your spring is sort of anchored to. Does that make sense? So it could have been anchored on the right side, right? But the sort of the numbers still work out the same way. If we move to the right, it's positive. If we move to the left, it's negative. Okay. And what this does, so what this equation does, f of x equal kx, what this does is it tells you the amount of force it's going to take to compress or to extend your spring, right? That's the force, that's the f of x that we're going to be using, okay? Cool. So now let me go ahead and do an example. These are pretty simple. Like I said, if I don't give you the K outright, I will give you enough information um, to find the K, okay? One more thing that I didn't really mention here, K is the characteristic value of the spring, right? So that's you, like I said, I'll give you either the K or I'm gonna give you enough information to find it, right? And X is measured in meters, okay? So now let's go ahead and do an example. Suppose it takes 120 newtons to compress a spring 75 centimeters from equilibrium. Okay. How much work is required to stretch the spring 150 centimeters from the equilibrium position? Okay. All right. So we need to first notice that I don't have a K. I don't have anything here, right? So we need to sort of describe uh, my function, my f of x here, right? So the first thing I'm going to do is this. We're going to go ahead and we know what that Hooke's law is supposed to tell us, right? Kx. Uh, we know that this is supposed to be equal to, right, 120 newtons, right? When we compress the spring 75 centimeters, right? So then this tells us we need to do this. So K times 0.75 is equal to 120 newtons. Okay, and if we divide this out, so divide by 0.75 divided by 0.75, our K is going to be equal to 160. So that means our spring, the force on our spring is going to be some 160 times X, depending on how far we move X, right? Okay, so now the question is this. How much work is required to stretch the spring 150 centimeters from the equilibrium position, okay? So our work, did I put the equation up here? Of course I did, there it is. Notice how the work equation goes. It's the force times dx, right? So we have our force equation. It's the 160x, right? And we need to compress this spring, stretch the spring 150 centimeters, right? So this is going to be equal to the integral 150 centimeters. This is where we have to keep in mind, X is measured in meters. So it's going to be 0 to 1.5 meters. That's 150 centimeters, right? Of 160 X dx. This is the amount of work that we need to do. At least we set it up as an integral. So now we got to solve this out. If you remember, right? 160, whoa, nasty 160. 160 x squared over 2, evaluated from 0 to 1.5. This is supposed to be equal to, I'm going to reduce some stuff down, 80 x squared, evaluated from 0 to 1.5. And this is 180 joules. So in order for us to stretch this spring out 150 centimeters, right? It'll take us 180 joules to do so. Okay. Next up is your quick checks. Go ahead and try these out. Like I said, follow the example. It's not too far off. All right. Moving on, because I do want to provide a fair amount of direction for these. These are pumping problems, okay? This last portion of this section is really going to require all the stuff that we just picked up to now from this particular section, okay? Now, I'm going to explain it a specific way, okay? The book explains it another way. They are equivalent methods of explanation, but I feel that my explanation is a little bit more intuitive than what you would find in the book. Okay, the book does this weird thing where it goes into negative X values, and I don't see the point behind that. At least the pictures show it going in negative X values. I don't see the point behind that. I'd rather go into positive X values if I can help it. That changes a little bit of their explanation, right? But all in all, right, both, like I said, both explanations are equivalent. They're both valid. This is just another construction of the same thing. Okay, so let's get started. Suppose we have a certain type of tank, okay, and it's full of a specific type of liquid, okay, and we want to pump out this liquid out of this tank, okay. That's what we're going to go ahead and find. So in these problems, for pumping problems, we are going to try to find the work required to remove water or a liquid from a container, okay. Now, like I said, I'm going to be doing a construction here, okay, and I'm going to be sort of doing this construction using a cylindrical cylinder, and this cylindrical cylinder is I'm using the cylindrical cylinder. I'm using the cylindrical cylinder because the geometry and the explanation comes a little bit more intuitive, right? Using the cylindrical cylinder, and then we can apply that knowledge outside. We can apply it to another type of shape. Okay, so that's why I use this sort of phrase right here. I might use it a couple more times while we're in calculus. Okay, without loss of generality. Okay, that means that I'm going to be building. I'm going to be building the sort of like the construction for how we're going to do these kind of problems, these pumping problems, right? Using a cylindrical cylinder, but the sort of like the logic, the explanation, um, doesn't get lost if we generalize this argument. Okay, that's what I want to say. That's what essentially is going to happen here. Okay. All right. So now There's a couple things that I want to sort of slap down on a piece of, like on a picture right now, right? Suppose we have a cylindrical container and that radius is r. So let me first slap down, let me choose my color. I'm going to do an X and a Y. Hopefully this moves. All right, it's not going to do it. I'll do it this way. Straight down the middle that way. I wonder if it'll do straight across. Yeah, it does do that. All right. I shouldn't have moved it. There we go. Okay. So I'm going to name this positive X direction. Okay. Just to give myself a direction. Okay. So now, suppose we have a cylindrical container and the radius for this thing is r. So from here to here, this radius right here, this is r. Okay. Our container itself, the entire thing from top to bottom, has a specific height h of c. So height container. Okay. And it's filled with a liquid. Okay. Let's go ahead. I'm going to draw it in blue in particular. So to denote that it's the height of the liquid, right? Okay. This right here is a height HL for my liquid. Okay. Okay. Our interval of concern is going to be this interval right here from 0 to however high my HL is. Okay. That is this strip right here. So this right here is from 0 to HL all the way up to that red spot right there. Okay. We are going to grab that strip from 0 to HL and divide it into regular partitions xi with width delta x equaling b minus a divided by n. Okay, we can grab this and we can start dividing this. We chop this up just how we've done in the past, right? In previous sections. Okay. Now, the question that we're trying to ask here, the question that we're trying to answer, right, is we want to find the work required to remove all of the liquid from this container. We want to find the work required to remove all of the water from this container. So the thing that we have to do, right, let me undo some of these, okay? So to construct our intuition, right, the idea here is this. We're going to try to find W sub I, okay, for moving or trying to remove the ith disk of water from our container. Okay, so what I'm going to do is I'm going to slap down. You guys see what I'm doing here? Here is my ith disk. I'm going to sort of go up to there. There we go. Here's my ith disk, right? So this is going to be my x of I. This is going to be my x of I minus 1. Okay, this is my ith disk of water. And what I'm going to try to do is I'm going to try to find an expression, right, that will give me the work to remove this ith disk of water. Okay. Okay. From the previous section, right, we know that work is given by some force times some distance, times some distance di, right? So the force is going to be given by a value somewhere between xi star, right? I'm going to need xi star, I'm going to find the force at that xi star, right? And I need to find how much it's going to take for me to grab that entire disk and move it completely out of the container. I need to find the distance that ith disk is going to move. That ith disk is going to move a distance di. So if you think about it, right, it's going to be from here all the way up to here. This is my di. Okay. So the explanation here is this. I need to grab this disk right here. I need to grab that disk and I need to completely pop it out of my container. The distance it has to travel is d sub I. Okay? Okay. So now we have f of xi times di. At least we have that much for the work, right? To determine my f of xi, right, we know the very basic of our equations. The force is given by some mass times acceleration, right? From our mass portion, right, we know that our mass is some density times V sub I, where V sub I is the volume of one of our disks, right? We're assuming here that our density is sort of constant across my liquid, right? So the only thing that's supposed to be changing is my volume, right? Okay. Since, and here's the part where we're not losing any sort of, we can sort of generalize this argument to any different shape, right? Since our disk and our whole shape is cylinders, right? We know that that VI is given by this right here, pi r squared times delta x. Okay, that is the volume of our ith disk. Okay, so now here comes the clumping up of everything that we just did. Okay, here we go. So our work from the beginning is some f of xi times di, right? Di will stay. The f of xi is given by some mass times the acceleration. Okay. And then last is our mi is given by that right there, the volume times its density, right? So let me go ahead and color code this a little better. Our mass is given by rho times pi r squared times delta x. Our A is our gravity that is acting on our liquid. And then our DI is the very tail end of the DI there. So in particular, what we're going to be doing, right, is the same argument as we've been doing in the past. We're going to grab all of these WIs, add them up, right? And whatever that summation is, that's going to be the work to empty out all of the water or all of the liquid from this container. Okay. Now, unfortunately, the calculations for the pumping problems always vary depending on the shape of your container, okay? So in this case, the shape of the container that I was using for the explanation is the cylinder, right? Depending on whatever that shape is, right? It doesn't have to be a cylinder, right? It can be a cone, it can be a sphere, it can be a cylinder, but with, you know, two semispheres on each end, right? Uh, all of those are completely valid for the shapes of a tank, okay? So the shape of the tank can vary. And because the shape of the tank can vary, right, there's no sort of flat out, there's no sort of flat integral uh, that we can use to find the work to empty out the tank. Okay. But notice that the argument that we've been playing around with, notice that the example or the construction that I made, right? I did it using a cylindrical tank, right? A cylinder, a soda can, right? But the argument itself still works out regardless of the shape of my tank. Okay. The only thing we do have to take into account is this right here, that the work is going to always be given by this right here. It's going to be rho times some VI times some gravity or times some acceleration, right? Times DI. Okay. And if you take a look, right, I'm going to be, let me erase this. There we go. This is my mass, right? This is my acceleration. And this is my DI, the distance to move a specific ice slice of water out of the container. Okay. The intuition from here on out, though, follows just as readily. Okay. The only difference is the container. So, how does this work out? That's what I want to go ahead and do an example for. So, these are common examples in engineering for sure. Okay. In thermodynamics and water flow. Okay. Suppose we want to find the work required to pump out the water of a tank that's in the shape of an inverted cone with height 10 meters and a radius of 2 meters, and it's filled up to 9 meters. I'm filling up this cone up to 9 meters tall, high, right? We're going to assume that the water has a density of 1,000 kilograms per meters cubed, okay? And the acceleration due to gravity is 9.8 meters squared. Okay, so here we go. Let's go ahead and start drawing in some stuff. So I'm going to go ahead and draw at least this much. Let me go ahead and see. I'm afraid to do it, but let's go ahead and try. See if we're going to, yeah, that's close enough. And I want to, oh my, oh my. Oh, I shouldn't have touched it. Let's try that again, huh? I'm going to go ahead and go from down here. Oh my. Okay, let's see if, that's close enough. That's fine. Okay. Oh, come on. Undo. There we go. I don't want to have that dot there. Well, that's fine. Okay, so what I want to do first is this. I know that it says my radius, right, is 2 meters. So that's this bit right here, out to here. This right here is going to be my 2 meters, right? The height of my cone all the way up to the top. So all the way to the top is 10. And it is filled up to 9 meters with water. So that height right there, that is 9 meters. And I'm going to put meters over here. All right. Okay. What I need to do now is this. I'm going to scroll down a little bit. I'm going to go ahead and slap down another X and a Y. Well, slap down another sort of axes. And there's going to be a specific reason for these. I'm going to draw without a depth. So I know this thing's going to look like this. If you take a look at it, right? You basically take a look at it from the side, directly from the side, not sort of like not above it, not below it, just straight across from the side, right? It's going to look something like this. Okay. This is still going to be my positive X direction, which is the same thing up here. This is going to be my positive X direction there, right? Okay, so I still need to sort of, this is the bits that I need, right? So I need some WI, it's going to be some rho times VI times gravity times DI, right? Okay, I need to fill in all of these bits, right? So if you take a look, right, let me draw in, first of all, let me draw in uh, a random ice disk. So I'm going to be playing around with this disk right here. Let me draw it a little better. Oh, come on. I don't want that. There you go. Okay. So I want to play around with this ice disk right here. Bam. Bam. There we go. There's my ice disk right there, right? So if you guys see, this is going to be my delta X, right? And this thing is going to have some radius outward, right? So this is going to have a radius outward. Okay. This is my, like I said, this is my ice disk, right? So now let's go ahead and start constructing my ice disk, the expression here. So I need the work to move this ice disk is going to be some rho times my volume for that ice disk, right? So it looks to be a cylinder again. It's going to be a disk of some sort, right? So this is going to be some pi r squared times delta x times gravity. I'm not going to play around with the gravity for right now, okay? Times di. Now, I need to move this disk, right? So now I need to put down this other x down here to match it, right? We know that this right here is my 0, and that distance up to here, from here, is x, right? I need to move this disk outside of my container, right? So I need to grab all of this and sort of toss it outside, okay? The distance for that to happen, whoops, not what I wanted. The distance for that to happen is going to be 10 minus x sub I, where x of I, right, is a point within that sort of little partition, that little chunk, right? Okay, so now everything's great except for this. I need an expression for R. Okay, and that's where I'm going to use the secondary triangle. I'm going to use a fact from geometry. Okay, so let me fill in a couple things. We know that this radius is 2. We know that this height from top to bottom is 10, right? Let me go ahead and draw in my secondary disk here. So I'm going to match up the red disk with the red disk. Hopefully you guys see that. Okay. So we have our two disks. And the thing that I'm going to be sort of playing around with, the thing that I'm going to need from geometry is the idea of similar triangles. In particular, the two triangles that I'm going to be calling similar are these. The big one, right? And the small one, this one. Okay. So now we know how far this is. It's 2. We know how far this is. It's 10. And we've already sort of assigned a couple things for the small little rectangle or the small little disk that we have right here. That this is going to be R and this is going to be a value X, right? So according to similar triangles, right? The ratios of the lengths should be the same. So AKA, if I grab my R distance divided by my X distance, right? If I grab those two things, they should be equal to, so R divided by X is 2 divided by 10. Now, why did I do this? I can get R is equal to 2x over 10, which is x over 5. This right here is what's going to be substituting in for my R squared up here. So now I have this as my expression, right? Rho pi, that's going to be my xi in this case, over 5 squared times delta x times g times the distance I need to move that ith disk, 10 minus xi. Okay, this right here is my final expression for moving my ith disk out of the tank. Okay. I have to do this for every single one of my smaller disks, right? And I need to do it for everything from 0 to 9, the amount of water that's in my tank. So the integral here will be this. It's going to be the integral, right, from 0 to 9 of all my wi's, right? My w dx's, which we already figured out. That's all of this. So it's going to be integral from 0 to 9. Rho is 1,000. Pi x over 5 squared times my gravity, which is 9.8, times my di, 10 minus x. And my delta x becomes my dx, so it's going to be dx there. This is the integral that I need to solve out. Okay, if we go ahead and do some of this stuff, so it's going to be, if you do some of the algebra that's in there, it's going to end up being 9,800 pi over 25 times the integral from 0 to 9 of x squared 10 minus x dx. So if you're unsure of how that I got that, it comes straight from over here. I just simplified a couple things, okay? I implore you, get good at your algebra. Go ahead and run through the steps, okay? And if you do this out, you end up getting 9,800 pi over 25 of 10x cubed over 3 minus x to the 4th over 4, evaluated from 0 to 9. And if you simplify this all the way, you should get, I'm going to put down the final answer, 972,580.536. Okay, so let me run through the argument really quick, right? I needed to find the work for the ith disk. So I had to sort of slap down an ith disk, right? Find the expression for the work to remove that ith disk out of the tank. Okay, and then if I grab all of those wi's and add them all up, I should get the work for emptying out the entire tank. Okay, that was the crux. That's how we got this expression right here, right? That was the crux of our argument. Okay, and notice that the only thing that changed from the construction to this example was the shape of the tank. That was it. Okay, and the way that we handled it was this way right here, right? So just keep in mind that when you go through the problem yourself, okay? The next thing I want to do here, the next thing that's up is a quick check. And this one is pretty similar to the construction of the one from right before. Okay. And this one's for everybody. So the whole entire class is going to be working on the same problem. And that's completely okay. All right. Besides that, I think I am done. The next thing that comes up is lecture questions. Okay. Try these out. If you're stuck on them, I've got office hours that you can come visit, and I have my all day times on Friday. Okay. Stop in, ask me questions. Okay. Besides that.